Okay, thank you very much. This is kind of like an old reunion in some respects. You've probably seen all the pictures of some people when they looked real young who were working in my group. That includes me, actually, you may have noticed. And also all the people out there who like to keep track of what Voyager's done. Really, really tremendous mission for which I'm just so happy to have been involved in back 40 years ago. It's hard to believe that, actually. So let me start out with just commenting on some of the publicity this event has received. I don't know if I can read all these here, but the media attention, NASA had a press release based on our paper, which was finally released last Thursday. And I think I spent most of last week fielding press calls from the press and just went on and on. Some of the comments, you know, to boldly go, you know what that means. It used to say we're man, but I think they changed that to either people or humans. Now we can say to boldly go where no spacecraft has gone beyond. And there have been really some astonishing comparison with our achievement, like the first landing on the moon. You could see in, I think it was the New York Times, like here, Ed Stone, circumnavigating the globe for the first time or having a foot put on the moon. Now, I'll have to tell you, it's a little bit biased with Ed Stone. He's the project scientist on Voyager, but he's pretty thrilled about this. So let me go on now. Bill and I decided we'd split this talk up, and since I'm a little older than him, I'm going to talk about the old stuff. How we got started in this mission, a little overview and that sort of thing. Then Bill's going to pick up with the latest observations, which we just reported in Science. So how did this mission get started? Well, in the 1970s, it was realized that the four outer planets, Jupiter, Saturn, Uranus, and Neptune, were lined up in just such a way with a single spacecraft launched at Earth, we could fly by all of those planets in one flight. And to do that, we had to make a very specific launch date in August, September 1977. The point is that these different planets go around the sun at a different rate, and it's only once every 180 years that you get the planets lined up such that you can carry out a flight like this. And luckily, I lived in the right era, and maybe we had the right background with all the things we did here in the department, starting with Explorer 1. I started working right after Explorer 1 as an electrical engineer here. That's 55 years ago, I think it was. So it was realized we could do this mission, and it was called the Grand Tour. And it was proposed to Congress, and it was turned down by Congress. And so what we did, we renamed the mission. It was called the Mariner spacecraft then, not the Voyager spacecraft. It was renamed the Mariner Jupiter-Saturn mission, and we lowered the cost. And that was approved by Congress. And it was funded in, I don't remember the exact date, but it was in the early 70s. And then there was a selection of instruments. These are all competitively selected instruments, and we proposed, and we lost the first round, I'll have to say, for some other instruments. But they finally realized the kind of thing we were doing, measuring radio emissions and waves in plasma, this ionized gas out there, was important enough to put the instrument on the spacecraft, so they took a French instrument off of the spacecraft. I'm glad I wasn't that PI. But so we did get on board, and we started building the instrument here in around 1970. And the instrument we ended up flying was not quite a carbon copy of an instrument we flew on a spacecraft called the Small Scientific Satellite. And frankly, I don't remember the year of the launch, but it was of that spacecraft. So let me go on to the next slide here. So let me talk a little bit about the spacecraft. Like I said, I'm going to do a bit of an overview here, how we got into this and everything. So here's a picture of the spacecraft, and here's a man or a woman, I can't tell which, in their bunny suit. They always have to wear these special gowns to keep everything clean. And it's really quite a big spacecraft. Weighs 1,790 pounds. I mean, you can look at the dimensions here. This high gain antenna here, that's the antenna we use for transmitting signals back to the Earth. Very crucial. We always have to keep that pointed back at the Earth. That's about 12 feet in diameter, just to give you a feeling for that. Electrical power, it is powered by a plutonium power supply. Electrical generates electricity. And they're located, those white objects over there, those are they call it an RTG. I guess they call it an RTG because they don't like to mention the word plutonium. But RTG, radioactive thermal generator, I think that's what that stands for. Now, an interesting thing about this, we don't have a picture of the spacecraft fully in its full flight configuration. And that's because the booms are not strong enough to hold it up in the gravity field. It's only after we get away from Earth in essentially zero-G environment that we can unfold the antenna. Transmitter is 22 watts, and I just had it reviewed for me recently that by the time we get to Earth now, it's 10 to the minus 19 watts, and we have to use to recover the signal at the NASA Deep Space Network. There are three antennas around the world, not three antennas, three locations. We have to use a 210-foot diameter dish antenna to recover the signal, and that's not good enough. It has to be arrayed for our special high rate data. It has to be arrayed with another 100-foot antenna. So we do recover the data. It has a computer on board. Incidentally, it's the first spacecraft that we built an instrument for that had an onboard computer. It has 68 kilobytes of memory. That is, yeah, I thought that was a lot of memory then. You have to remember when my HP 65 handheld computer, it had 50 program steps. So, and that computer has been absolutely crucial for many things. Just to give you, I got to be careful not to talk too long about this stuff here because we want to get Bill up there talking about our most recent stuff. But for example, at launch, it was not realized how long a time exposure and that you'd have to take when we got out to like Uranus and Neptune, which is the light intensity is very dim out there, and the spacecraft moving fast enough that if you take a 4-minute time exposure, you get blurred images, just like taking a picture of a race car at a racetrack. And so they invented a scheme where they could use the computer to send commands to the gas jets on the spacecraft to slowly rotate the spacecraft to take out correct for the image, and that was never contemplated at launch. So I guess there are 11 instruments. That's counting the transmitter, which is regarded as an instrument because they use the radio signal for certain types of like radio occultation things. But there are really 10 actual science instruments on board, and only 5 are now operating, actually powered, I should say. It isn't that they failed. It's like we're so far out, there's nothing to take pictures of, so we turn the camera off. And we have to turn the camera off because it's using electrical power, and we're getting pretty far down on the power curve. So those are a few comments about the spacecraft. Now let's talk a bit about the instrument. We use this 2 long antennas, this one and this one. They're 10 meters long, and someday I'll tell you about how we actually erect those antennas. There's a little mechanical device in there that extrudes them out. A real clever thing invented during World War II, actually. It was a tank antenna. And made by, let's see, Fairchild, I think it was. Anyway, our instrument is, it's basically a radio receiver mounted at the base of those 2 antennas, and it's that box right there, and there's a gold-plated mock-up up here on the bench, which you can come up and look at if you want. We have a spare instrument here in the department, but we've been reluctant to take the lid off to show people. We have, in some cases, done some tests on that instrument to measure things that we either forgot to do or in the way of calibration. Weighs 1.4 kilograms. When we were selected rather late to finally fly the instrument, they gave us, I think, that's in pounds, I think about 2.5 pounds or something like that. We were told we have to build an instrument weighing no more than that. And we take 1.1 to 1.6 watts, certain mode here. Now, why should we make these measurements? Well, for radio, it turns out Jupiter, Saturn, Uranus, and Neptune, I mean, when we launched, we knew Jupiter was an intense radio emitter. And there was a lot of interest in studying that. So that's our first thing, study radio waves. We also study waves propagating in the plasma. This ionized gas up there, just like I'm speaking with, there are sound waves in this gas. We call them ion sound waves. If you want to learn more about that, you can take my class in plasma physics if I teach it next year. I don't know. When I came back from Stanford in 1964, that's why I was hired back here, was to teach plasma physics. Okay, we actually built, there were 2 spacecraft, Voyagers 1 and 2. Back in those days, we used to almost always build 2 spacecraft. And do you know the reason for that? Right. Sometimes the rockets didn't work. And back in the early days of the spacecraft, when I first started working here, I mean, it wasn't even 50%. But that's gotten much better recently. And it was launched on a Titan 3E-Centaur, the upper stage with a Centaur, and that was the highest performance vehicle we had. It was actually had higher performance than the Saturn V. Higher performance in the sense you could get a higher launch velocity. And I don't think we have a vehicle now that can do what that rocket did. So when you have two launches, your best strategy is to launch the first one as early as you can in the launch window. And that, if you launch then, you don't get quite as high a performance because of the trajectory, the way the trajectory works. So Voyager 1 passed Voyager 2. Okay, now here's the trajectory we actually flew. Sun's in the middle, the Earth is there, and you see the 2 launch dates there. And now I told you in the beginning there that the main purpose was the grand tour, to go to Jupiter, Saturn, Uranus, and Neptune. Well, Voyager 1 did not do that. We flew to, let's see if I can pick out Voyager. Here's Voyager 1. We flew to Jupiter and then Saturn, and we didn't go on to Uranus and Neptune. And I'll tell you, here's the reason. Saturn has a big moon called Titan. And Titan's about the same size as the planet Mercury. But the interesting thing about Titan is that it has a dense atmosphere, a nitrogen atmosphere. Pressure 1.5 times the pressure in the Earth's atmosphere, even more dense. We have a nitrogen atmosphere, mostly, some oxygen, fortunately for us. But Carl Sagan argued very strongly that because it had a dense atmosphere, it might have a greenhouse effect, and the temperature might, in fact, be up to something like where living things could exist. And when we got to Saturn, we went by Saturn in such a way that we could get to Titan. And when we do that, you can't go to Uranus. It was one or the other. And so we went to Uranus. And Titan, you might get on Google and type in Titan and go learn about it. It's an amazing place. It has lakes of ethane and propane. Some of the people in the audience are nodding their head. Yeah, it's a really, really strange place. Lots of petroleum. It does. It's true. However, no oxygen, so it won't burn. Okay, so that's the flight plan. And Voyager 1 ended up, I think, I haven't really checked out exactly why, but we had a higher velocity. Okay, I should tell you something else. Voyager 1 is now going 38,000 miles an hour. It's the highest velocity object ever made by a human. And it wasn't just the performance of the rocket. We also used gravity assist at Jupiter. The swing-by effect, slingshot. The planet's going along like this. We flew behind it, and gravity kind of slings it out. And we did it again at Saturn, and that's how we got up to 38,000 miles an hour. I guess I should tell you another thing too. This gravity assist allowed us to get out to Neptune And I believe it was 12 years, if I remember right. 89, we launched in 77. Yeah, that's 12 years. If we did not have gravity assist, if we didn't have this lineup of the planets, it would have taken 30 years with our best rocket to get there. So we cut the flight time down from 12 years to 30 years. I mean, that's worth doing, as far as I'm concerned anyway. Okay, now I'm really not going to give you, I can't take the time to give you a whole story about the outer planets, but you know, I teach astronomy once in a while, and maybe there's a fourth of the astronomy book is full of, well, I'm looking over here, some other people that are recently teaching astronomy. I used to emphasize this. You know, pictures from Voyager. That's all, because before that, all you'd see is a telescope at Earth, and you couldn't, well, you could tell that Jupiter had 4 moons going around it, the Galilean satellites and so forth. But we took all these tremendous pictures, and not only the planets, but also the moons. And I've just picked out some of my favorites here. I'm not sure, it's probably like 60 different moons we took pictures of. I'm not sure the number. But these are the Galilean satellites, Io, Europa, Ganymede, and Callisto. That one has volcanoes on it. It's the most volcanic object in the solar system. And at Neptune, there's an interesting moon called Triton, and it apparently has geysers coming up out of the surface. You know, can you see the slides okay? I could turn the lights down. You think it's okay? All right. All right. Now, I talked a bit about the pictures we took at Jupiter and so forth. I just have to tell you what our instrument did. You know, what kind of sounds do we detect? Well, here's one. I have to explain a few things first. Jupiter has a tremendously strong magnetic field, 10 times stronger than the Earth's magnetic field. And we have this plasma ionized gas coming out from the sun called the solar wind, and it's moving this way. And when it runs into this big obstacle, this magnetic field, it forms a shock wave out here, just like a bullet going through the air forms a shock wave out in front of it, or a supersonic airplane. And this is in this ionized gas, and it creates a huge amount of turbulence right at the shock wave. And I'm going to play the recording as we go through the shock here. And you'll see this is a frequency time spectrogram, we call it. This is 0 kilohertz, and there's 8, so that's at the upper level of your hearing probably. And this is 10 seconds. So what I'm going to do is play this so you can hear it, and a cursor will go along and tell you where you're at. Now I'm going to tell you one other thing. See that oscillation up there at that specific frequency? That gives us the density very accurately, and Bill Kurth is going to talk about that, because that is what ended up telling us we're in the interstellar medium. So let me play this now. Anyway, it just goes on and on. Now, I don't know, you know, you can't see a shock wave. Even an aerodynamic shock, well, sometimes you can see them with refraction of light. But I like to play this in the plasma physics course, and it gives a certain reality to the physics of shock waves. Because in this shock front, there's a huge amount of turbulence that heats the plasma at the shock and so forth. So come take my plasma physics course, if I teach it next year. Now, I'm going to tell you another thing that's a big deal in our life at Jupiter. As we flew by Jupiter, we heard some whistling tones. You see up here? Frequency, time, and whistling tones. Now, I did my PhD on what are called whistlers, but not at Jupiter, at Earth. They're produced by lightning. So when we heard this tone, and I'll play it for you, you can just barely hear it. So everybody be quiet. We knew that there was lightning at Jupiter. And this is the discovery of the first object in the solar system other than Earth. We know we have lightning here, but this was the discovery of lightning at Jupiter. This is a picture taken on the, taken on the dark side of Jupiter. And that's the limb of Jupiter, you know, the sunlight just getting over the top. And here, incidentally, the camera took these pictures after we discovered it. I want to make that perfectly clear. This is a lightning flash down in the clouds at Jupiter. But you want to guess, Jupiter is 10 times bigger than the Earth, just to give you a scale. It's a huge thing. You want to guess how big that is from one edge to the other here?
Diameter of the Earth.
Diameter of the Earth. You're in the right ballpark. It's like from Los Angeles to New York. And these are called super bolts. They put out Jupiter has a lot of lightning, and we are also in the business of studying lightning storms at Saturn. I won't go into that. Now, after the Voyager 2 Neptune flyby, well, the question is, you could say we want more money, but we got to have a good reason, right? So a plan was developed to try to reach interstellar space. And the mission was renamed the Voyager Interstellar Mission. See, we had 3 phases in this. We had the Mariner, Jupiter, Saturn. They gave us money for that. And then when we got to Saturn, it was renamed then the Voyager Uranus Neptune mission. So we get to Neptune and we say it's now the Voyager Interstellar mission. What do we mean by reaching interstellar space? That's the next topic of my talk here. Let me tell you some other things about this. We are now, with Voyager 1, out at 125 astronomical units. Astronomical units is the distance between the sun and the Earth, just for scale. Other ways of explaining how far out we are, it takes 17 hours and 20 minutes for the radio signal to go from the spacecraft to our antenna on the ground. Now, I don't know if that impresses you or not, but it certainly impresses me. Because here's a story, here's a thing I'll point out. How many of you remember the astronauts landing on the moon? Quite a few, quite a few. Right, we're in a kind of a similar age group, I guess. When mission control would ask the astronauts a question, there was a noticeable time delay. Not much over a second, but maybe 2 seconds round trip. See, it's round trip. And that was the first time I would say in my life that I could perceive the time delay due to the propagation of light. Actually a radio wave, but they travel 186,000 miles a second. All right, so 1 second roughly to the moon, a little over that. We're out there at 17 hours. Astronomers like to measure distance in light years. Right, Phil? Lots of light years. A light year is how far light goes in a year. The closest star is Alpha Centauri at about 4 light years. Well, we're not out a light year, but we're almost a light day. I like to think that's a pretty big achievement, right? At 17 hours, pretty soon we'll be at a light day, and we can put that in astronomy books, can't we, and start measuring it light days. Okay. Now, after we left Neptune and flew out, farther from the solar system, this picture was taken in 1990, and it was called the picture of the century. And so what we did, we looked back toward the solar system, and I don't know if you can even see it here. I can't read it, but that one, let's see, I'm going to have to go up closer here. My eyes aren't all that good anymore. Here's Saturn. There was a frame taken there, and it was blowing up here. The background was changed, and you can see Saturn. You can see, I don't think it was quite all the planets. We couldn't get Pluto. And of course, it's not a planet anymore, right? So it's Neptune. Okay, Jupiter, Earth, we got Venus, Saturn, Uranus, and Neptune. But I don't think we had Mercury in the picture. It's just the concept. It's like looking in the rear view mirror of your car as you're going away from someplace, and you can look back. Okay, let me get more serious now about what we did recently. To explain what we mean by the interstellar space, or I'm going to call it interstellar plasma, because that's what we're really studying, this ionized gas between the stars. I'm going to have to start out and talk about the solar wind. If you look at well, I think it's white light, they take this picture and blank out the sun, you can see these kind of streamer things coming out. And that was realized that it looks like a wind coming out from the sun, and it's called the solar wind. How many people here have heard of the solar wind? I hope almost everybody. A lot of people have heard of the solar wind. That's good, because I won't explain it anymore. Except it is, because the sun is so hot, this hot gas is streaming off from the sun, and because it's about at the surface, at the corona here, it's about 1,000,000 degrees. So it's really hot, and at that temperature, it's completely ionized. You can't have a neutral gas at that temperature. So here we're talking about plasma now, ionized gases. And it flows off at about 400 kilometers per second. To put that in normal miles per hour, that's about 1,000,000 miles an hour. So it's going off at flowing out from the sun at a really big clip. Now, about 50 years ago, something like that, people started asking the question, well, what happens to the solar wind as it flows out from the sun? You know, does it ever stop out there or what? Well, the issue of where it might ever stop is determined by the interstellar gas pressure. You see, as the gas from the sun expands, it keeps expanding into a bigger and bigger volume. So its density has to just keep going down and down and down. So it has less and less ram pressure. That's the pressure if you put your hand outside of a car when it's moving, you know, you can feel the pressure in your hand. And someplace out there, there's this, we always anticipated there's this gas between the stars that we call the interstellar medium. Someplace out there, that solar wind is going to have to come to a stop. And that is what we call the heliopause. And that is what we're after, actually, and what we just penetrated through, well, actually about a year ago, but only now have we actually figured out we did it. And that was the part that that's what we did. So heliopause, a new word. Also, I'll tell you another word. The heliosphere is that region of hot solar gas coming out from the sun. We have a new word for that we call the heliosphere. Now, let me tell you more things about this. Maybe you'll learn more than you ever wanted to know here. But I forgot to bring out a Geiger counter here. Okay, it's too late, huh? Yeah, well, I could. I'll tell them. Let me talk about cosmic rays now, a little bit. Now, you probably know about cosmic rays. If we had set a Geiger tube out here, it would go click, 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 click. There's these particles, these really energetic particles going through the Geiger tube, and they're going through your body all the time. And they're important. For example, they cause mutations in your DNA. They probably play a role in evolution by causing mutations. Well, it turns out that they found, and James Van Allen, who the building's named after, this is what his interest was. Back when he arrived here in about 1955 or 50s, I can't remember the year. It turns out the cosmic ray intensity varies slowly in time over an 11-year cycle. And that is lined up almost exactly with the sunspot number. You know, there are sunspots, and they vary on this 11-year cycle. And in particular, here's how we thought it works, and we know this much better now, that the solar wind during solar maximum, that's what we're kind of in right now, actually, when there's a lot of sunspots, these sunspots, if they get too close together, they cause explosions. They call them solar flares. And that stirs up this solar wind, and especially the magnetic fields in it, and makes all kinds of turbulence here. And the cosmic rays come in and they snake around in that turbulence and they get scattered, and so the turbulence kind of keeps them out. So during solar maximum, the cosmic ray intensity is lower. The message here is that the solar wind is actually protecting us to some extent from the cosmic ray flux on the whole system. And Van Allen was very interested in that, and he flew an instrument on Pioneer 10 and 11 And the whole point of the instrument was to, that was another spacecraft flown, actually launched before Voyager. It was to measure this, what we call cosmic ray gradient, distance from the sun and how the cosmic ray intensity varies. And the thinking was that as you go out from the sun, someplace you'll get to the heliopause. See, I use that term, and at that point, you're in the pristine cosmic ray flux that's incident on the whole system. So that was his interest, but unfortunately, Pioneer 10 and 11 ceased operating. I think it ran out of power, and I can't remember the years, but it was quite a while ago. Voyager had a better, more power and so forth. Now, here's another thing to explain to you. The sun is moving relative to the interstellar plasma. So if you sit in the sun's frame of reference, that plasma is flowing in like this, and the heliopause, which is labeled right here, this is a simulation actually. The heliopause is kind of a bullet-shaped boundary separating the hot gas coming out from the sun from what we think is the relatively cold interstellar plasma. Now, it turns out, by good fortune, Voyager 1 is heading out this way, and Voyager 2 is heading out this way. And like this drawing shows, we just got across that boundary, and Bill will give you the explanation of why we concluded that. Now, here's a picture of a star near the Orion Nebula, and this star is immersed in a very high-speed gas flow. And Phil, I don't know where that gas flow comes from. Do you? Have you seen this picture before?
Yeah, I think it's more the star moving.
Star moving relative to the, yeah, I wasn't quite sure actually. Anyway, you can see a boundary here. And that is kind of the equivalent of our heliopause. There's another star up here someplace. Can anybody else see there's another one? That's why I thought it was an overall flow of gas by these stars, but I actually, I'm not a card-carrying astronomer, so I don't know how to answer that question. Okay, now, how far to the heliopause? The problem was we didn't know the interstellar gas pressure. That's really hard to measure, especially when you're not out there. And people have tried to guess at that and so forth, and I'm just going to list here the distances to the heliopause that people thought. Back in 1956, 5 AU, that's right at the orbit of Jupiter. And there's all kinds of people that published papers here and numbers all over the place. Even Lanzarote, good friend of mine, and Schultz in 1969, he published 5 AU. And there's other people here. Even my colleague and I, we made a mistake. I will admit it. We forgot about the fact that there's a contact discontinuity there. That was a huge mistake we made. And Van Allen was getting closer, but here I published with Bill Kurth and some others a really big number in 1993. That's 20 years ago. Mark that. 20 years ago we published, and I'm going to tell you how we did that. I hope I'm doing okay on time. Let's see, that's about 40 minutes. I better hurry up. Okay, how did we do that? Well, we have this antenna on, our instrument, and we heard in about 1983, and Bill discovered this over here, a radio emission that we didn't know where it was coming from. We weren't near any planet, and I'm going to play this for you. And there's a long gap in between, but you can hear it. And this is the actual frequency that we detect on the antenna, so you can hear it. And we call it the 2 to 3 kilohertz radio emission. Pretty evident. Can't miss that. We didn't know where it was coming from. We thought it might be a planet that we didn't know was producing this thing for some reason. We even thought perhaps that it might be some interstellar, like a pulsar or something like that. That would have been a very big discovery, although our discovery was nonetheless very important. Now here's a big event. You can hear little events happening. 1992, we got this really big event. Still didn't exactly know where it came from, but well, we did in 1993. Right there, we finally explained it. So I'm going to tell you how we explained this. Okay, I have to tell you about coronal mass ejections. During solar maximum period, which we're sort of in right now, you get these huge explosions on the sun. And I'll run a video here from a spacecraft called SOHO. You can look this up, just type SOHO into Google, and you can see there's a spacecraft that's staring at the sun, looking at these pictures. And you'll see these explosions. I'll call them explosions. They're called coronal mass ejections because they ejects a huge amount of material right out of the corona of the sun. So let me play this now. Hopefully it'll run. Pretty big ones in there. Notice all those speckles around here? Those are energetic particles come from the sun, causing, when it hits the detector, it affects the, puts a charge on the detector there, like your CCD camera. Those are the kind of things that'll hurt astronauts if you're out there in space. I mean, that's what it goes right through the thing. Now, there are times that happen when you have a whole series of these explosions in like a month, and the sun's rotating and everything, so it just starts spewing out all these things. And those things produce what we call a shock wave. And the shock waves from these different explosions, if you get out far enough, just merges into one huge shock wave. And the reason is the slow shocks get overtaken by faster shocks, and they merge. They coalesce into a single big shock wave. And I try to show this here that, not only that, around the shock here, there's lots of turbulence, and it causes the cosmic ray intensity to go down. That's called a Forbush decrease, and Scott Forbush was here for a while in my very early days here in the department. He's a very famous guy because he discovered the Forbush decrease. And actually what the Forbush decrease tells you is there's just been a big shock wave has gone by the Earth. And when those shock waves go by the Earth, they also increase the aurora, brighten the aurora. They cause magnetic storms. They've even caused the lights to go out in cities because of the change in the magnetic field. It induces a voltage in the power line and knocks out power systems. So, they got some potential importance to humankind. And here is actually that same 1991 event. The solar flares occurred right here. We saw the Forbush decrease at Earth. And then we had 4 spacecraft out there, Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2. And they were all at different distances, and we saw the time at which that front went by the spacecraft. It's pretty obvious, see? And from that, so we knew there was this tremendous blast came out from the sun. We could measure the speed just by, how far out you were and the time it went by, and it was about 600 to 800 kilometers per second. I didn't turn that into miles per hour. It'd be several million miles per hour. Then what happened is 400 days went by, and we detected the radio emission. And here that shows it explicitly. These are the 2 most intense Forbush decreases ever observed. And see here, 412 days went by and we saw the radio emission. Same thing over here, big blast out from the sun, 1 solar cycle later, by the way. 419 days, we saw this big event. So I postulated, actually my colleagues and I, we postulated that what happened was the shock wave was propagating out from the sun. We saw it at these 4 spacecraft out there. We could measure its velocity. And finally, when it got to the heliopause, it produced the radio emission. In other words, the shock ran into this density wall out there and produced the radio emission. So guess what? I can compute the distance. The distance is speed times time. 600 or 800 kilometers per second times 400 days. We got a big number. 116 AU to 177. Now we were at about 40 then, and nobody wanted to know this answer. Nobody wanted to believe this answer, because one of the problems was that meant it would take 20 years until we got there, which is exactly what happened. And they were afraid they'd turn the funding off and say, 20 years, we can't pay for that. And so there's lots of people, we voted at meetings like how far it's going to be, and it was all, you know, much closer. In fact, you can only almost plot the distance at these meetings we had as a function of time, and they would go out right with Voyager's distance. Well, I'll tell you, we were right in 1993. And here's another plot I'm going to show you here. This is for the 1993 event, 20 years ago. This is a plot of plasma density over here. Now, there's this oscillation in the plasma that Bill will talk about, and the oscillation frequency is directly related to the density. And so here, and it's called the plasma frequency. Now, as you go out from the sun, as I told you, the density goes down and down and down and down. And right here, the solar wind is supersonic, and it has to go through a shock transition. And we detected plasma oscillations there, and they were at 300 hertz. And then what we expected, okay, we postulated that that shock hit the cold interstellar medium, and it emitted a frequency here at the plasma frequency. This oscillation in the plasma is the same oscillation frequency where you get the radio emission. So we could measure that frequency. Remember I said 2 to 3 kilohertz? 2. You convert 2 to density, and it'll be a little bit below 1/10 of a particle per cubic centimeter. That's actually 100,000 per cubic meter. It makes the number sound better, bigger, if you think cubic meters. And so this was, I believe, really, in my view, the first actual measurement of the interstellar density. You know, it's where we first made a, and that was, and then there were some other measurements started to support this. So everybody pretty much expecting the interstellar plasma density, which up to this point was largely unknown, was about 10 to the minus 1 particles per cubic centimeter. So at this point, I'm going to turn this over to Bill. And that was, let's see, the termination shock crossing was 2004. That was 9 years ago. And for 9 years, we did not hear any plasma oscillations. And I was getting pretty depressed. So I guess, Bill, I'll give you this. So you're going to tell us what went on then. Let's see, let me help you put that up here. Okay. All right, now things should be all ready to go there. Okay.
Okay, I've got a bet going here that you've got one more slide. That's okay.
Oh, did I forget to show a slide? I did, didn't I?
Okay.
Yeah, that's the termination shock crossing in 2004.
Yeah,
right.
These are magnetic field observations by the Voyager magnetometer as we cross this shock. And this shock occurred at a distance of about 94 astronomical units. So that's 30 astronomical units behind us.
Right.
Okay, so now we're going to fast forward. In the last 9 years, our instrument on Voyager 1 has detected nothing, zilch, absolutely nothing. Almost a little bit more than a year ago today, Don and I went out to a meeting at the Jet Propulsion Lab of the Voyager Science Steering Group meeting. Happened to be on the occasion of the 35th anniversary of launch also. And we were seeing data like this. This is data that if you come to Tom Cremegis' talk on Thursday, he'll talk about these. I should say that Tom is also an alumnus of the University of Iowa. He reported that these very energetic protons, these are greater than 211 MeV, these are galactic cosmic rays. They jumped up to the highest level they've ever been measured. And for the last several months, they've stayed up there with very little variation. There's also some somewhat lower energy particles that are generated in the solar wind, in the heliosphere, and they dropped like a rock, and they haven't been seen since. Now, there's a number of boundaries here where things kind of went up and down. Turns out there's a total of 5. The last time we crossed this boundary was on August 25th, 2012, just a little bit more than a year ago. So here's Don and I. We're going to this meeting, and everybody's talking about, wow, look at this. All the galactic cosmic rays jumped up, and the solar wind particles went away. What'd you guys see? Nothing. Well, if you study galactic cosmic rays and energetic particles, and you don't pay attention to anything else, you'd say, okay, we must have crossed this boundary that Don talked about, the heliopause. What didn't happen, though, is we didn't have a plasma instrument on board Voyager 1. There is one, but it's one of the few instruments that's failed over time. It actually failed shortly after the Saturn encounter in 1980. If that instrument had been operating, they could have made the measurements with that instrument that we've made more recently. And they would have seen an increase in the density, we think. But they didn't have that measurement. The only other measurement they had that they thought might tell us something about what's going on is a magnetometer. And a lot of people, me included, thought that once we crossed this boundary, the magnetic field would change directions from what it is inside the heliosphere to what we think it is outside in the interstellar medium. Well, that didn't change. The intensity went up a little bit, but the direction didn't change. So, being careful scientists, the science steering group for Voyager decided we've crossed a boundary. We don't think we know enough right now to call it the heliopause. We should wait. Now, fast forward from last August to April. These are the data that we saw in early April and extending through into May. These are data from part of the instrument that Don talked about. This is what we call our low-rate instrument. It's a series of, we have 16 channels. Each looks at the intensity as a function of time in each of those frequency channels. We haven't seen anything in these channels for 9 years. Nothing. And now all of a sudden, starting in early April, we start seeing a signal at 3 kilohertz. This channel is fairly broad, so we don't know exactly what frequency it is. It gets to be fairly intense. It's very bursty. And you heard Don talk about this, these radio emissions coming from plasma oscillations beyond the heliopause. This is exactly the frequency we expected to see them. They show the same temporal variability. We looked at these data and said, this is it. We've crossed the boundary. We're now in the heliosphere. Or, I'm sorry, we're now in the interstellar medium. And you might say, okay, why didn't we see these earlier? Well, you also heard Don talk about these coronal mass ejections that caused the radio emissions back in '92 and in 1983. Well, it turns out on March 7th of 2012, this is what that same spacecraft, the SOHO spacecraft, saw. That blast wave is another coronal mass ejection. I have to tell you that Don's video showed you about 4 days worth of data, so it was just spewing off all the time. This is just a couple hours worth of data. This blast wave left the sun at a speed of about 5 million miles per hour. Now, it slows down as it goes through the heliosphere. We think its average speed ended up being about 625 kilometers per second, or probably 1.5 to 2 million miles per hour. And you can also see these energetic particles hitting the CCD of the camera, just as in the video that Don showed. So we think this is the trigger from the sun that propagated all the way out to the heliopause and caused the waves that we've now detected. Okay, now Don played you sounds of the bow shock at Jupiter. And that uses the other part of our instrument. This is a much more high fidelity receiver. It gives us much higher frequency and time resolution. And the problem with these data, though, is it takes a lot of data. We can generate 115,000 bits every second. rate back from Voyager now is 160 bits per second. If we really crank it up, we can send these data back at 1400 bits per second. Do any of you remember using a 1200 baud modem? That's exactly that's our highest data rate back from Voyager. Okay, so we get now in these panels, each one of these panels has a time scale of 48 seconds. And we get one of these little blips of data about every 3 or 4 days, a couple times a week. So here's one on day 102, 105, 109, 112, 116, 123. So we get these little snippets of data that gives us a lot more information. And what we're looking at are these very narrow band emissions. I should say, to be fair, that there is a line here at 2.4 kilohertz that shows up no matter what's going on. That's the power supply frequency on the spacecraft. So that's kind of an, you could call it an interference tone, or you could call it a calibration tone, whatever. Okay, so I'm going to play the sounds from just one of these snippets so you can hear what it sounds like. Okay, well, we always get people, excuse me, we always have people ask how this works. How do we get sounds from space? And so I've got a little cartoon here to try and explain that to you. So we start out with the plasma that has electrons. These are the little green minus signs here. Ions, they're the plus signs. And you have to realize that the electrons are a lot less massive than the ions. So if something moves, it's the electrons that moves first. Now we have a radio on Voyager, and Don said my antennas are too short, and I agree, Don. We should have longer antennas on Voyager. Instead of 10 meters, we should have 100 meter or 1,000 meter antennas. Van Allen Probes has 100 meter antennas, and boy, are they sensitive. So we got a radio. The radio is going to produce a waveform. Then we take that waveform. There's a big gap right here. It's about 125 astronomical units. But we get the data to the ground. We run the waveform into an amplifier and speaker. And by golly, sound comes out of that speaker. And it's because these electrons are sloshing back and forth. This is actually the mode of oscillation that we're detecting in the interstellar medium. Okay, now I mentioned that we only get a few of those snippets a week. This is now a 1-year time period, and we've taken all those little snippets and put them side by side. And this is the event that we found this spring. When they played the tape recorder back, I think it was on April 23rd, we found out, well, gee, we got data starting way back here, and here's another event. This event didn't even show up in the other part of the instrument. It was between two of our channels. It was lower amplitudes. It was just kind of hiding from us. Otherwise, we could have started getting excited a lot sooner. But the next thing we recognized was that these frequencies were increasing with time, and this emission was increasing in frequency with time. In fact, you can draw a straight line between the two events, and it connects them pretty well. We've actually measured the slope. Everything looks great. If you extrapolate backwards now to about 1.9 kilohertz, and that's this frequency that the radio emission that Don talked about, that's the lowest frequency we see it. Look what day we end up at. August 25th. August 25th is a very special day because that's the day when all these energetic particle guys were talking about the galactic cosmic rays increasing and the solar wind energetic particles going away. So our claim is that since these look like they're on the same slope, and that if you extrapolate that back to August 25th, it's a continuous line, we think the spacecraft is moving through a density gradient, so that these frequencies are increasing as a function of time. And we're measuring the same ramp in frequency that we expected to see on the basis of the radio emissions that we detected earlier. Now I'm going to play this. I should say that this video you can find on YouTube, and it's been downloaded 2.1 million times since last week. So I think that meets the definition of going viral. I've cheated and taken the 2.4 kilohertz band out of here. With these very high resolution measurements, we can actually, for each one of those 48-second blips of data that we get, we can very accurately measure the frequency. We've done that. We've plotted those here on a scale. And there's that same dashed line. I should say that I've got a query from somebody out in New Jersey who wants me to send this data to them so that they can give the problem to their 8th grade algebra class of doing a linear regression of these data points and calculate the same thing that we've done here. I think it's a great exercise. We've done it. We've done it, but I am going to send them the data, yeah. Yeah. Okay, so let me just say a few words about what's going on here. I've got a little cartoon that shows this density gradient that we think we're in. And I've plotted here what we think the shock looks like that's moving out through the plasma. And I've tried to show that it's moving out here. This shock is a source of electron beams. And these are beams that stream into this upstream plasma. And that's the source of free energy that makes the electrons wiggle. That's what turns this thing on. And so for a period of space ahead of that shock, we detect plasma oscillations at the frequency of this density gradient. When this shock overtakes the spacecraft, then they turn off. And we don't see them anymore. And just to go back to this picture that Don showed you, this little ramp in frequency right here is where we think the spacecraft is now. We've gone through this big jump in density, and now we're in this pileup region right here. I should say a lot of people have predicted there's a pileup region out there. I would say nobody agrees that they understand why that pileup region is there. And let me just go back. This is a more complicated plot than I want to talk about, but I wanted to plot the radio emission from 1993 and show the upward drifting frequencies that we saw in 1993 and this upward drifting density ramp that we're seeing now. Now we've cheated, we've changed the time scale. The reason we've changed the time scale is that the spacecraft is moving out at a speed that's slower than the shock we think that's moving out. There's a shock that's moving through this density gradient faster than Voyager can. And so it doesn't take it as long to excite waves over this full frequency range as Voyager does actually measuring them in situ. So I don't know if any of you go to the festivals downtown. So this is our bucket list. But see, I think there is one higher on the list that I had to exclude. It wasn't for consumption. Anyway, I'd like to join Don in thanking all of you in the audience who have worked in our group, who've worked on this project. It's been a terrific ride.
You're having fun.